Hi everyone, here we are for the second part of the lesson 1.4. Remember that we are looking at polygons, the general definition, and we looked at congruent polygons and just the pieces of polygons, including what does it mean to be consecutive, as well as looking at diagonals. So for this part of the lesson, we are going to define equilateral polygon, equiangular polygon, regular polygon, convex polygon, and concave polygon. These are part of your definition sheet, but if you notice, I haven't fully filled them in. What I would actually like you to do here is try to see if you can come up with your own definition. And here's the nice thing, is that I've kind of given you part of the definition to start with. A good definition classifies and differentiates. So all of these definitions are going to start with a polygon, which makes sense. What I would do is pause the video, try your best to come up with what you think a good definition here is, and then restart the video and double check. Conversely, you can also just follow along with me. It is good practice to write a good definition. In this example, equilateral polygons, we notice we have a bunch of different types of polygons. So we have triangles, pentagons, quadrilaterals, hexagons. And then we have also those same types of shapes in this next piece. What is happening though is that what do all of these things have in common? And then of course, looking at the name, we notice that all of the sides here are congruent. And so in each of these polygons, we have all congruent sides. All of the sides are congruent. In this one, for example, only 2 of the 3 sides are congruent. In this counterexample, these 2 sides are congruent, but these 2 sides are not congruent. And so we can conclude then that the definition of an equilateral polygon is a polygon with all congruent sides. Pretty straightforward. An equilateral polygon is a polygon whose sides are congruent. When we go to look at special types of quadrilaterals, we will notice that we have 2 types of equilateral quadrilaterals, squares and rhombi. And then we have 1 type of equilateral triangle, an equilateral triangle. Our next definition I have here is an equiangular polygon. Again, looking at this, these examples, we have triangles, we have quadrilaterals, we have pentagons. So we have all different types of sides, numbers of sides, and we also have all of the angles are marked as congruent. In these counterexamples over here, or these things that do not follow the definition, excuse me, not counterexamples, in this triangle, for example, only 2 of the angles are congruent, but not the third. And in the other examples, none of the angles are marked as congruent. So we can conclude that an equiangular polygon is a polygon whose angles are congruent. In a quadrilateral, we have rectangles and squares are equiangular quadrilaterals. In triangles, we only have 1 type of equiangular triangle, and that is actually an equilateral triangle, which we will get into in a second, because when we put both of those things together, being both equiangular and equilateral, we get what we call a regular polygon. Our examples here show every one of these polygons has all congruent sides as well as all congruent angles. If we look over here, this polygon has all congruent angles, so it fits that part of the definition, but not necessarily all congruent sides. This polygon over here has all congruent sides, but it doesn't have all congruent angles. So we can again conclude that a regular polygon is both equiangular and, not to give anything away, but I think you know that the type of equilateral quadrilateral is a square. So a square is both equilateral and equiangular. A very common regular polygon, another very common regular polygon that we see a lot is like the classic hexagon shape. That's sort of the beehive honeycomb shape. It's like beehive. That doesn't make any sense. The honeycomb shape. And another example of a regular polygon that is very common is a stop sign, which is a regular octagon. So those are some examples of regular polygons that you are probably very familiar with. Our last two, you might not know as much. Our first one is convex and our second one is concave. And I actually want to look at these both at the same time because if you notice, convex polygons and not convex polygons have the same examples for concave. I'm not saying this correctly. The examples for one and the non-examples for one are reversed when we're looking at the second one. Maybe that makes more sense. So what this tells us is that convex polygons and concave polygons cannot be overlapping in any way, shape, or form. You can't be convex and concave at the same time. If we look here, the big thing happens to be looking at the diagonals. In a convex polygon, all the diagonals, anytime we try to connect or make diagonals, they always occur inside the shape. In a concave polygon, we have a diagonal, at least one, that occurs outside the shape. Remember that a diagonal connects two non-consecutive vertices. So for our last two definitions, which just happen to be at the top, a convex polygon is a polygon with no diagonal outside the polygon. That's how we're going to define that. And a concave polygon is a polygon with at least one diagonal outside the polygon. My little tip and trick for remembering this is a concave polygon makes like a little cave. So basically one of these little pieces kind of bump in, so to speak, and you can like make a cave. So that's how I remember that. This concludes lesson 1.4. Just like in the other lessons, I would encourage you to go and do the homework from the book, or at least do some sample problems. Check your answers in the back. I also encourage you to keep track of any questions you might have so that when we meet together, you are going to be able to get your questions answered and I can support you as best I can. Great job on this lesson.